Good morning. So it is time to move on to chapter 27. Give me 1 second here. So chapter 27, we are looking, in this chapter and the next chapter, we're going to be looking at magnetic forces and magnetic fields. So the front cover on this first slide that's coming up here, what they're demonstrating here is this is a wire with current running through it. There's an I there, so it must be current. So we have current running through this wire, and we can see that there are kind of these circular patterns that have been set up. It's some kind of material that's responding to the magnetic field that the wire is generating. So when we have current going through a wire, something like this, it's generating a magnetic field. What we're going to find is anytime you have charges in motion, in addition to generating electric fields, there are also magnetic fields that are generated. And we'll take a look at it. It's a little more complicated than what we saw with the electric fields, but let's look at some familiar stuff and then maybe focus on a couple of kind of misconceptions about magnetics. So, and if you'll notice, I tend to use the word magnetics instead of magnetism. Magnetism, unfortunately, has a kind of a different meaning also. So magnetics kind of rhymes with electrics and electric forces, magnetic forces, all of that. Anyway, if we look at what we think of as just a magnet. So most people have played around with magnets. They've, had magnets that repel each other or attract each other. And kind of what we learn is that magnets have, two poles. So poles are not the same thing as electric charge, and we'll see why. Sometimes there's an effort to try and draw some similarities. I want to try and create some distance between those concepts. Everything we talk about in terms of magnetic forces and magnetic fields is in terms of the charges we have already defined, the electromagnetic charge. So these poles are just kind of handy ways of keeping track of how the effect is oriented. We'll see how that works. So let's say that we've got a couple of magnets and we've identified their so-called north ends and their south ends. And what we find is that the north ends push away from each other and the south ends push away from each other, but north and south attract. Now, what is it that's going on inside here? And very quickly, in a piece of magnetized iron or nickel or other ferromagnetic materials, what we have is the possibility of electron spins becoming aligned. So in most materials, all the materials around us have electrons. And electrons have charge, and they also have angular momentum. So quantum mechanically, including charge and angular momentum, means that you generate magnetic fields. I mean, in general, charges in motion are going to generate magnetic fields. So what we have in a north-south orientation, for example, in a piece of magnetized material, is we have electrons that, instead of all of their spins canceling out, in a piece of iron, for example, it's possible to get some portion of the spins aligned in a particular direction. So the picture that we have right here, let's say we have electrons spinning, let's go down to the attractive case. What we find is if we tend to have electrons in each of these objects whose spins line up in the same direction preferentially, two spinning electrons spinning in the same direction attract each other. There's a magnetic force that draws them towards each other. If I have two electrons and one is spinning one direction and one is spinning the other direction, they repel. So that's kind of interesting, right? And we'll see how that works, but basically that's what's going on with the north-south stuff. The north-south stuff is just keeping track of orientation of the preferred spin direction for the electrons. We'll look at some more diagrams here. So if we step back and take a look at magnetic fields versus electric fields. These are kind of the fundamental diagrams. Now, there's always this question with textbooks as to what gets included and what doesn't get included, and I feel like this is an important step to make sure gets included when we're thinking or we're learning about electric and magnetic fields. If you remember back to chapter 21, in chapter 21, we had drawn kind of a standard diagram here. Here is a charge located at some point, and what we're doing is we're coming out some distance, and the distance that we're coming at is given by r. So r is going to, and I didn't get that labeled on the diagram, it should be in there, write that in. So we should have an r right there and say I've come out to some point, I'm going to call it point A, and I'm coming out a distance r, and when I come out to that point I'm going to get an electric field with a magnitude of kq over r squared, where k is our electromagnetic force constant, and attached to that I've put a unit vector. So with electric fields and now with magnetic fields, almost always we're going to be thinking of magnitude and direction separately. They're part of the same package, but determining the direction versus determining the magnitude are usually divided up into two separate processes. So for example, with the electric fields, we say, hey, it's the kq over r squared, that part gives us the magnitude, and then the unit vector will keep track of directions. Now I put an angle in here, but it turns out the electric field for something at rest, it doesn't depend on angle. It's uniform in all directions. Now let's see how that compares with a magnetic field. So in order to have a magnetic field generated, the charge either needs to be moving with some velocity or it needs to have an acceleration. So velocity and acceleration are going to determine how large the magnetic field is. Now, quickly going back to the electric field, we might ask, well, what happens if the charge is moving? Does the electric field go away? Does it stay the same? And for electric fields, this is the basic formula for a charge at rest. This is its electric field. If the charge goes into motion, there is a small variation in the electric field. If the charge goes faster and faster, that variation gets larger. And when you do get to high speeds, when you get to speeds, a significant fraction of the speed of light, we still have an electric field. It doesn't follow this simple formula. So kind of our approach in Physics 4B is we're going to assume all the charges that we're looking at when we're calculating their fields are either at rest or they're not moving too terribly fast. Okay, so but velocities and accelerations of the charge are needed to get a complete description of what the electric field and the magnetic field is like. So kind of the first order effect from charges in motion. So notice on this side I put a velocity here and I've got an angle here, and the magnitude of the magnetic field is given by kq over r squared. Well, so far it looks the same as the electric field. Oh, but there's a factor of v over c. And remember, c here is the speed of light. That's 3 times 10 to the 8th meters per second. It's a really, really high speed, at least from our everyday experience. That seems like it's a really high speed. And it turns out, you may ask, well, why is the speed of light showing up in these formulas? And it turns out that what we call the speed of light, this value c, is ever so much more than just the speed of light. It's actually a constant that tells us how space and time are put together. So I always feel like this. I always feel like discussing electric and magnetic fields, it's almost like we should do special relativity first and talk about space-time and how they're related. And it turns out I'm trying to make the formulas as analogous as I can. I'm trying to line them up side by side to see the differences. It does turn out that once you've done a course in special relativity, you can rewrite these field equations in a much more unified manner. So anyway, for what it's worth, but it's usually felt, and I think that's correctly, that you can't really spend a semester or a year learning special relativity and then come back and do electric and magnetic forces. So for those of you who are moving on, say, physics majors, or if you have, if this is an area you're interested in, if you take upper division classes in relativity and then upper division classes in electric magnetic forces, you'll see all of that. Anyway, don't want to get too much into that. So kq over r squared, kq over r squared, that's the first factor. Magnetic fields have this extra factor of v over c. And that says that typically the magnetic fields are smaller than the electric fields are because of that factor of v over c. V over c tends to be a really small factor. So, and there is no such thing as going faster than c. So that ratio is always something between 0 and 1. It can't go lower than 0. If it's at rest, it goes to 0. If it's going as fast as it possibly could, then it's asymptotically approaching 1, but it never becomes greater. All right, now this direction information, instead of just one unit vector, we have to use a cross product of two unit vectors to show what direction the magnetic field is in. And it's a little more complicated, it's a lot more complicated, but you guys can get it. So it is a cross product. If you remember from Physics 4a, we've looked at cross products, and we said that to determine directions for this, we could use a right-hand rule. Now there's right-hand rules in the book with fingers moving around and stuff, and again, there was a student who showed me this right-hand rule years ago, and I've just decided, I think it's the easiest way to think about it. If you put vector 1 as your thumb, and then vector 2 as the direction of your fingers, and you just hold your hand out, there's no moving fingers or whatever, then your palm is facing in the direction of the cross product of those two vectors. So that's not bad. I mean, my hand makes up a plane, and my thumb represents one of those vectors in that plane. My fingers represent the other vector in that plane, and my palm faces in the direction of the cross product. So let's take a look and see how that would work. If I'm taking the cross product of the velocity unit vector with the radial unit vector, well, the velocity unit vector is a vector that has magnitude 1, and it points in the direction of velocity. So here is my unit vector for velocity. Now I can move it around anywhere I want in order to calculate the magnetic field, but I do have to maintain its orientation. And since it's a unit vector, its magnitude will always be 1. So that's what we're looking at for that unit vector. Now the radial unit vector is where it was before with the electric field, but now I've got to take the cross product. Now I've got my left hand up there, and unfortunately it's not a left-hand rule. It's cross products are defined in terms of right-hand rules. So I could use a left hand, but let's not do that right now. So what I want to do is I want to get V cross R, and that says there's my hand, and there is the velocity vector is in that direction. The radial vector is here. My palm is facing in the direction of their cross product. So the magnetic field is coming out of the page, out of the board. Now, if I move around to different locations on my imaginary sphere that I've outlined at distance r, what that's going to tell me is that, well, if the magnetic field is coming out of the board here, it's going to be going into the board here. So if I'm looking for how the magnetic field is oriented, what that's going to give me is it's going to give me loops of magnetic field lines surrounding that center line, which is where the charge is traveling. So the charge is located here. It's instantaneously, at some instant, it's got a velocity in this direction, and what that's going to create are looping magnetic fields surrounding the path of the velocity. Now we talked a bit about how electric and magnetic fields propagate at a finite speed. They propagate also at the speed of light. And that says that the instantaneous effect of the charge right here will create an influence that spreads out at the speed of light. And as that influence spreads out, it's a done deal. It's independent of what the charge does in the future. So once the charge has generated that portion of the field, it moves on to the next location and then generates the next portion of the field that will propagate outwards. Okay, now one complication, I'm going to be saying that a lot in these next couple chapters. One complication here is that when I take a cross product of unit vectors, it's not 1 anymore. So unit vectors, when we take the cross product, actually create a factor of sine theta, right? Cross products are magnitude vector 1, magnitude vector 2, times the sine of the angle between them. And since they're unit vectors, their magnitudes are 1, but there is a factor of sine theta. So let's see how that affects things. You can see what theta looks like right here. If I was looking at a point right in front of that charge, there's no magnetic field. The magnetic field is going to drop off at a point right in front of where that charge is located. As I follow this spherical surface, what I'm finding is I'm seeing these looping magnetic field lines. And as I move at larger and larger angle, I find out, oh, that's where the magnetic field is the largest. If I'm only considering a spherical surface where all the points are the same distance, so what we're doing is we're taking into consideration the distance effect, then what I find is that the largest magnetic fields are here. There's a zero magnetic field in front and behind, and then there's everything intermediate in between. So not all of these loops are the same in terms of magnitude. So as this charge goes by, its field, if we're measuring the field moves along with it. The field keeps up with that charge as it's moving by. Okay. All right. So that's kind of an interesting effect. So what that tells us is that the magnitude of the magnetic field, kq over r squared, so far it's the same as the electric field, but wait, there's 2 changes we have to make. First of all, we have to put in a factor of v over c, which says if the charge is just sitting there, there's no magnetic field at all. As it goes faster and faster, the magnetic field gets larger. Now the other factor we have to consider is this sine theta factor. And so it's going to depend on the angle. So it's going to depend on distance, how fast the charge is going, and what angular direction we're looking at relative to the motion of the charge. All right, now the third item that changes this is, look, I put a factor of c over here on the magnetic field. Was that a misprint? Was there an error that I made? Now I'm going to take the factor of c away just for a second and say, look, that B symbol is what we use to represent the magnetic field. Sometimes we call it the B field. So we find ourselves calling it the E field and the B field for magnetics. It turns out that for historical reasons, we use different units for magnetic fields and electric fields. But we actually understand, and we've understood this for a long time, that electric and magnetic fields are really part of the same package. So, in fact, going back to special relativity again, there's just one formula that will tell you, it'll give you all of the electric and magnetic fields combined, and in one formula rather as 2 distinct formulas. What we're seeing here are kind of low speed approximations of different portions of that one formula. So in order to make the units match up, we have to put a factor of c back on. Now that's just for side-by-side comparison. When we actually get into calculating the magnetic field generated by a moving charge, then what that gives us is, well, I have my factor of kq over r squared. Uh-oh. I left out the r squared. So the r squared goes right here. I apologize. I'll need to get that written back in. So what we do have though is we have the K over C. There's a second factor of C from here. That becomes K over C squared. Factor of Q, factor of V, factor of sine theta, and that invisible factor of R squared that's underneath there. So make sure you get that written down. Now, I tried drawing the loops, and I don't know how successful that was down here, but that's the idea. So this is my magnetic formula, or my magnetic field formula, for a moving charge, moving at velocity v, and it has a factor of r squared missing, but make sure that gets written in. So that's kind of, I can do the side-by-side comparison then between those two formulas. All right. So that's it. That's the fundamental stuff. Now this is actually not in the book, but it's just something I like to refer back to, because this is where it all starts from, is looking at individual point charges. So let's go back and look at those magnets then. And what we were saying is, here's a magnet, and here's the north end, and here's the south end. And you know, if you split a magnet into, if you cut it in half, you don't have a north end and a south end. What you have is two magnets, and each one of those magnets now has a north and a south end. And again, that's because the north and south is really just keeping track of orientation of the spins of the electrons in that piece of material. So with magnetic fields, we said that they could be generated by charges with linear motion. Either a velocity or an acceleration is enough for a charge to be generating a magnetic field. It turns out that rotational motion, well, that's also going to generate a magnetic field. Because if I have a charge that's spinning, if I look at individual pieces of that object, I have charge that's in motion. It's circulating in a particular path. So there's kind of two different views of this. There's the classical view. So for example, we can get a wire and we can get current going through it. I could get a current loop, and that current loop is definitely going to be generating a magnetic field. And we can use kind of standard formulas that we saw on the page before to integrate over the entire effect of that current loop. In fact, we'll do that probably in the next chapter. But another thing that could happen is you could have a fundamental particle like a proton or an electron or even a neutron, it turns out. They all have spin, angular momentum, and the electron and proton have a net charge. The neutron is also made of charged particles. It's made of quarks. So the protons and neutrons are made out of quarks. Those quarks are charged. And their magnetic fields actually are attributed to the individual spins of the quarks. So if I have a charge and it's spinning, I put a little omega down there to represent spin, that's also going to generate a magnetic field. And the shape of that magnetic field is something like this. Now you may have seen pictures of this, certainly in a textbook. They have a number of diagrams where you see magnetic fields. It's actually what we call the dipole configuration. So back in chapter 21 we looked at electric dipoles and showed what the electric field looked like. And now we're looking at magnetic dipoles and the fields that they generate. And to generate that shape, it's the shape itself that's referred to as the dipole. All I need is a spinning charge. It doesn't have to be a pair of charges like the electric dipole. One charge spinning is enough to generate that dipole effect. So that's what's going on in magnets. Every electron has a little magnetic dipole field, every proton, every neutron. The electron effect dominates. So in materials, it's the electron dipole effect that creates magnetism, the largest portion of magnetism. And in most materials, all of that cancels out. So the same way that all the pluses and minuses cancel out and give us a neutral piece of something, it turns out that their spins cancel out. Now, even in atoms or materials where there are leftover spins, if I look from one atom to the next, those spin effects will cancel out. So that's what's going on in iron. Iron has 2 or 3 leftover electrons that are spinning in the same direction for an individual atom. But in unmagnetized iron, those effects are going to cancel out. Now, in a piece of a magnet, the spins now are aligned and they actually maintain that alignment. And so once I get some number of electrons aligned, I can cut this into pieces, and those individual pieces maintain that alignment. And that's how we define north and south. So north and south is just in terms of alignments for the spins of the electrons. And this is just a repeat of what we've been talking about here. So there's the north-south. I've got all these electrons that are spinning like this, and each one of all along the length of this. So as I start to break it into smaller and smaller pieces, that spinning alignment is maintained. And then you'll see pictures like this in the book too. So here's a magnet. These are iron filings. And it turns out that when you place pieces of iron, unmagnetized iron, in a magnetic field, they become magnetized. So the iron will respond. The electrons will begin lining up, and then once they do, they get drawn into an alignment with the field. So it's often used as a nice picture to show the magnetic field lines that we have. And then the compasses too. So the compasses have been magnetized and they're responding to the field. So here's Earth's magnetic field. Now, the Earth has a rotational axis, and so that's what we've got shown right here. Rotational axis of the planet. It turns out that our magnetic field looks kind of like a dipole. So the shape of our magnetic field is similar to what it would be if we just had a uniform bar magnet, a big bar magnet, a really big bar magnet, sitting inside the planet. Now, it turns out that the orientation of that is tipped. It's, boy, how far is that? It's like 15 degrees or something. So the orientation of the magnetic field doesn't line up with the orientation of the rotational axis. And that's kind of interesting. We do think that the magnetic field is sustained in part by the rotation of the Earth. The rotation of the Earth it creates the possibility of electric currents showing up inside the core of the Earth. There's a lot of iron. There's a solid iron core, and it's surrounded by a molten iron outer core. And we think that in the outer core, currents of charge get set up and maintain the Earth's magnetic field. But that's an active area of research, is how do planets generate their magnetic fields and what sustains them? Why don't the magnetic fields drop away? So magnetics it's a really interesting field when applied to these planetary and stellar sorts of situations. And I guess another thing we're supposed to pick up from this is the way that compasses were defined. So compasses were defined as, the north end points north and the south end points south, roughly, relative to these magnetic field lines. And what that tells us is that then at the north, generally within the region of the north pole area, is actually the south magnetic pole. So the south magnetic pole and the north magnetic pole are opposite to the rotational axes, north and south. All right, good to know, right? And here's just another picture showing, it's giving a bit of an idea as to how we might generate a uniform magnetic field. So in a lot of the problems that we see, we just write down and say, here's the magnetic field, here's what it looks like. And this is an example. What we've got are the field lines exterior to the magnets, are defined in a way that they run from north to south. So that's a good thing to keep in mind too, is that directions of magnetic and electric fields, there's a little arbitrary nature to that. There's other ways that they can be defined. We define them as vectors and try and keep them as simple as possible. So, but it's just one of the possible definitions that we've used. All right, this is showing again that if we have current traveling in an electric wire, that's going to generate a magnetic field. Think about that. If I have individual charges moving, those individual charges are generating magnetic fields. And that says that if we get a bunch of charges all moving along a wire, that's certainly going to generate a magnetic field. Now in this case too, since we have current at all locations along the wire, we'll get these magnetic field loops, and this is a good picture showing those magnetic field looping lines. For a long wire like this, we'll just get kind of a symmetric set of loops along the length of the wire. If the wire is bending, then we'll get loops around wherever the current is bent. But and then one more picture here, and they're trying to get some directions defined. We'll see how this is determined. But instead of a straight wire, what this is showing is I can also generate magnetic fields using loops of wire. And that's actually very common when we want to generate a large magnetic field concentrated in a certain region. What we can do is we can get not just one loop, but many loops of wires. And that will give us a concentrated magnetic field in that region. All right, one more look at charges and how they affect each other. So electromagnetic charges, they create electric and magnetic fields, and they also experience force. So it turns out that each of these charges, let's see where they are here. So I've drawn in a couple charges, Q1 and Q2. These are two charges, and they happen to both be in motion. They're both moving along in some direction. I'm going to say this has velocity v1, this has velocity v2. Now we know that since they're positive charges, they're both positive, there's going to be an electric force that is pushing them away from each other. And we've seen that in chapters 21 primarily. And now what we'd like to do is ask ourselves, well, these electric and magnetic fields, what do they depend on? They depend on how much charge there is. They depend on what the velocity of the charge is. And it turns out they also depend on acceleration. The acceleration effects, we'll see that in some later chapters. So for now, we'll just have charges moving along. We'll think of how fast they're traveling. And what's happening here is charge number one, and I've drawn charge number one again here. Charge number one has all of these looping magnetic fields surrounding it as it moves along. Now, if I look at the orientation, it's a positive charge here. It's traveling in that direction. And from our diagram, what we saw was that's going to give me magnetic fields that come out of the board, above, and then below the charge, they're going back into the board. Now, what that says is charge number one is generating its magnetic field. And there it is. There's the formula for the fields. Here is the electric field being generated by charge 1. Here is the magnetic field being generated by charge 1. And now what we want to do is introduce the forces. How much force is a charge going to experience in a magnetic field? And it turns out that the force that charge 2 experiences is going to be determined by how much charge it has, what its velocity is, and what the magnetic field is that it's passing through. So by the time, I've got the electric stuff written up here too, but we can kind of ignore the electric stuff and concentrate. Charge number 1 is generating a field, and charge number 2 is experiencing a force due to that magnetic field. Those are the two steps that we've broken this down into. And so here's charge 1 moving along. It's generating a magnetic field that is into the board. Now here's another cross product. So it's saying that the direction of the force is going to depend on the velocity direction of the charge and on the orientation of the magnetic field it's passing through. So, time for a right-hand rule again here. So here is the velocity direction. The magnetic field at that location is into the board. So if I think of velocity as the first vector in that cross product, the magnetic field is the second. My palm's facing up. So it says as two charges go along, positive charges, they're repelling each other through electric forces, but the magnetic forces are actually drawing them together. Two charges moving together in the same direction, the magnetic effects are actually drawing them together. Now, if it's two individual charges, then the electric effects are going to be much larger than the magnetic effects typically, and that means that the electric effects will dominate. But what we'll see is, instead of two individual charges, what if I have two wires? If I have two wires and there's current 1 going through this and current 2 going through this, well, wires are electrically neutral. So wires don't exert electric forces on each other, and that means that the magnetic effects will become dominant. When we have two wires with current parallel to each other, there's actually a magnetic effect drawing those wires together. So, kind of interesting, good to know what these effects are like. And here it is. So what we've got then is, they went to the hardware store and got one of those 22-volt batteries that's industrial. And they're running current through a magnetic field. So that's like a whole series of charges going through that magnetic field region. And this is the end of the, it's the ends of this curved magnet. And so the magnetic field lines are running from north to south. So what that's showing is, hey, look, what we've got here is a magnetic field that's oriented in that direction. And then I've got current passing through in this direction. And the force equation, which they don't have here, we'll write it down. The force is going to be the cross product of this. So what's happening here is that the velocity, which I'm going to use for my thumb, the velocity direction is here. The magnetic field is, if I think of the velocity or the current as into the board, magnetic field lines are across this diagram, then the force from that is downwards. Now, if we reconnect the battery in the opposite direction and send the current back the other way, now we're going to end up with a force that's upwards. So, now there may be a concern here saying, well, wait a minute, the current doesn't really consist of positive charges. The current consists of negative charges going the other way. Well, in any of these formulas, any of these cross-product formulas, fields, and forces, I know you're always warned, never use a left-hand rule in cross products, but I do. If the charges are negative, you can actually play around with using left-hand rules instead of right-hand rules. The left-hand rules work really well for negative charges. But, if I have positive charges going in the direction we've defined for current, that creates the same effect as having negative charges going the opposite direction. And that's what we have with electrons. Those are negative charges going opposite to the direction of current. It's going to create the same force direction in all of our diagrams. Okay, so this is the basis for electric motors. If I can take current, send it through a magnetic field, that wire is going to experience a force. We'll see more examples of this. So here it is, finally. They got the formula here. Maybe we could have jumped ahead to this before. So the force that we're looking at is given by the current times the cross product of this length vector times the magnetic field vector. Now when we just go for the magnitude, that cross product formula turns into this. I get a factor of I, a factor of L, a factor of B, and a factor of sine theta. The units that we're using for the magnetic field, so we haven't talked about that yet. The units of a magnetic field are the Tesla. So 1 Tesla is, well, they've got it here as a Newton per amp meter. It's the same thing if you think of electric fields. Electric fields were in newtons per coulomb. Teslas actually have an additional factor of velocity units, meters per second, that they have to cancel out. So Teslas are newtons per coulomb divided by meters per second. And that combination gives us what we have here. So the standard unit for a magnetic field is Tesla. We also use the Gauss. A Gauss is 1/10,000th of a Tesla. So a lot of times magnetic fields are fractions of Tesla, and Gauss gets used, but I'm going to say use micro Tesla instead. Let's not introduce more units than we really need. So here's an example that makes use of all of these effects. So it says this. It says I've got a magnetic field, it's in place, it's being generated by something else. So there's something generating this magnetic field, and what I'm setting up here is I'm taking a wire, running it through the magnetic field, and then I'm turning on some kind of power supply. So now I have a wire that I've placed in this magnetic field. I'm going to send current through that wire, and I want to know how much force will the wire experience, and what direction would that force be in. So here are the numbers that they've given us. So they're saying that the current going through is 30 amps. That's a good amount of current. And the length of the wire through the magnetic field is 12 centimeters. Now let's think about what that length would mean. They've got it set up really well in the diagram here. What they're saying is, well, here's where the magnetic field actually is. The magnetic field is limited to this region, and so the wire will only feel forces in the region where the magnetic field is. When the current's running through the wire, that's when the force will be generated. So we've got 30 amps of current, we've got a length of 12 centimeters, and then the wire is tipped. So in this direction, the wire is tipped at 60 degrees, as shown in the diagram. The magnetic field is uniform, and it's at 0.90 Tesla. Okay. So how much force is acting on the wire? And the first thing we could do is we could go for directional information. So what direction would the force even be acting in? And what we can do is we can go back to the idea of V cross magnetic field. So I can treat the direction of the current as the velocity direction. So that's my velocity direction. Now I'm going to turn my hand like this. So that's the direction of velocity of my charges. I'm treating the current as a bunch of positive charges going that way. Magnetic field is here, and my palm will face in the direction of the force. So this wire is going to get pulled into the board with the current orientation that we have. Again, if I'm using a right-hand rule, I'm working with current, and if I think of current as a bunch of positive charges going in the direction that the arrow indicates, then thumb is in that direction, fingers are in the direction of the field, V cross B will give me the direction of the force. Now, as far as getting the numbers, let's get the numbers figured out here. So let's come back. Now, this is the formula they've just given us. They're saying that the force is determined by how much current and the length of the wire in the magnetic field. And then the vector signs here are keeping track of directions for us. So what I put in parentheses just below is, well, this is the force acting on a current, but this is the force acting on an individual charge. So again, I want to relate this back to why is it happening to the current? Well, the current is a bunch of charges. And if I just look at one of those at a time, how much force is each one experiencing? And it's this formula right here. Force is equal to how much charge times its velocity times the magnetic field that it's passing through. That's going to determine how much force there is. So before we get to the problem, let's look at maybe an easier orientation. Let's say that we have a magnetic field. I put a bunch of X's up here, and the X's represent the orientation of the magnetic field. Turns out in many examples, the easiest way to orient the magnetic field is to have the magnetic field going into the page. Once we're working with these cross products, it's kind of inherent in the problem that they're going to be three-dimensional. We're going to have diagrams that can keep track of 3 dimensions. And so putting the magnetic field into the page often is an easy way to take care of one of those directions. And so that's what I've done here. Now I've put the magnetic field into the board here, and then I'm going to send current through this wire from left to right. Now what's happening here is that I can use either one of these formulas. If I think of this as a series of charges all moving in some direction through a magnetic field, then I can do V cross B. So the V is the direction the charges are moving in, B is into the page, and the force is going to be in this direction. Now we can combine a bunch of charges and just think of it in terms of a current, and then I get the equation above, but it works the same way. So in this case, the L vector is defined as the direction of current. So it's a little funny here. Instead of having current have a vector sign on it, we actually use the displacement, or the path of the current, to take the vector information. So the vector information, the directional information, is assigned to the length instead of to the current. All right, let's see. I think I made up some numbers here. For this particular problem, let's say we have a 2-meter length, we have a magnetic field of 5 Tesla, we have a current of 4 amps. What's the angle? You know, I kind of left out the sign theta here. And what we're going to find is the same thing we did with before when we were looking at angles of the field is if the two vectors are right next to each other, if they line right up, that gives us 0. And if they're perpendicular, that gives us 90 degrees, and that gives us the largest value for our cross products. What's happening here is I've got the velocity in this direction, magnetic field is perpendicular, that's 90 degrees. So at 90 degrees, the cross product factor, the angular factor, just becomes 1. So I've left that out in this calculation, but putting all these other numbers in, I ended up with 40 newtons. Now that's a really large magnetic field, 5 Tesla is huge, and 4 amps is it's a pretty good sized current, and that's a pretty good length of wire. And this 40 newtons, you know, 2 meters is going to be like this. So along that entire 2-meter length, I've got 40 newtons, and that force is evenly spread along the length. And that's why I drew a bunch of little force vectors. So force, 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 force. The 40 newtons is spread out along the length. It's not like it's all concentrated at one spot. There's a little bit of force acting along the entire length there. Okay, that's, I hope, is a simpler diagram, and these are our formulas. Let's come back then and look at that problem that they had just given us. So that was on the page before, and now I've drawn that. So here is the wire passing through the magnetic field region, and this time the magnetic field is oriented differently, right? This time the magnetic field is oriented across the page. I have a wire that's traveling, it's carrying current at some angle. They tell us that angle is 60 degrees. The length of the wire, they told us, was 12 centimeters, and the current 30 amps and the magnetic field 0.9. Now what we already looked at with the previous diagram, we already determined that, well, the direction's down here. Let's go ahead and pick up the directional information. So here is the direction of the current. Here is the direction of the magnetic field. The L vector is in the direction of the current. and my magnetic field is in the direction of the magnetic field, that gives me a plane containing those two vectors, L and B, and my palm is facing in the direction of the force. So all along here, there's going to be a force pushing that wire into that magnetic, or into the board with what we have drawn here. Putting all the numbers, so I can throw all the numbers into the formula that I've got here, and I ended up with 2.81 newtons. Okay. Well, the length one's, it's not nearly as long as the other previous example. The magnetic field is quite a bit smaller. You can kind of see the differences. Okay. So a couple good examples looking at forces on wires. Now here's one more. What we've got is, well, we're getting a chance to see all different orientations of the magnetic field. That's good. So in this case, those little circles with the dots in the middle, that means the magnetic field's coming out of the page. I always feel like drawing X's is easier than drawing all those circles, but it's kind of X and O's here. X is into the page, O's are out of the page. And this time, we've got a loop of current. We can see the entire circuit here. So there's some kind of a hook holding this thing up, which is kind of interesting. So we got a hook, we've suspended a circuit. Now look, the circuit even has a battery in it. So there's a battery in this circuit, oops, wrong way, maintaining current, that was the positive terminal, maintaining current through the loop. So I've got this steady current going on now. Now as we turn up the current, what's going to happen is we're going to have a larger and larger magnetic force here. Now first of all, let's figure out what direction the force is in. There's a couple possibilities here. It could be the force is pulling down on that loop, or it could be that the force is lifting up on it. Let's see which it is, and it's a right-hand rule. Current, magnetic field, force. So the force is going to be coming out of my palm. And if the current's going this way, let's see if there's a way to orient my hand. Is there? Oh, there it is. Yeah, sorry. What you can do, what I used to carry around, I don't have one with me right now, I used to just get some little popsicle sticks and make a mutually perpendicular set of popsicle, tape them all together. You're allowed to bring that to the exam. So, and then I have vector 1 written on one of the sticks and vector 2 on the other, and then the cross product, so that I don't have to go into all these different contortions to try and figure out these right-hand rules. Let's see, so current is going this way, but the magnetic field is coming out towards you guys, so that means the force is down. So yeah, that's the direction of the force, and again, it's going to be distributed all the way along here. Now I'm also going to get forces along the sides, but that effect is going to cancel out. So that's what the drawing looks like. Now they've given us some numbers. They say that in particular that length that runs horizontal is 10 centimeters. And they said that the force that we're getting, it's a small force, 3.48, 10 to the minus 2 newtons, and the current, they're saying the current is 0.245. So let's take a look at this example. So we already took a look at the directions of the force. We said that when the current's running, there's going to be a force acting on this portion. There's going to be a force acting here. You can try out your right-hand rule for that. The force acting along here in the opposite direction. Now up here there's no force because there's no magnetic field. So it's only those lengths where the magnetic field actually is located, where we're going to have magnetic forces pulling on these currents. These forces on the side, because of the symmetry in the problem, that's going to cancel out. So if all I'm looking for is a net force, it's really this force along the bottom. This is not being opposed, at least not by any other magnetic force. There is a tension or a upward force holding onto the circuit that's opposing that, holding it in place. Let's see, for that bottom region, current is going in this direction, magnetic field is out of the, again, it's this, the force in that direction. And then, the F net, again, is just due to the bottom portion. I can use this formula. And again, I got a 90-degree orientation. And where that 90-degree orientation is coming from is, I've got current in this direction, magnetic field is coming out. Those two guys are at 90 degrees, right? So at 90 degrees, the sine of 90 will be 1, and I don't have to show that factor explicitly. What's left is the force is ILB. I started to put some numbers in here, but I realized we're actually solving for B in the problem. So I came back and solved this for B. I put in the force, I put in the current, I put in the length. And it says that the field is, the magnetic field is 1.42 Tesla. So that's how large the magnetic field would need to be to create the force that we're measuring. All right. Ooh, this one looks more complicated. So in this one, I've got a couple of straight regions of current, and along with that, a couple of straight regions of current, and then along with that, I've got this curvy portion right here. And again, we can go in and we can use right-hand rules and try to determine how much force we're going to have, where the force is going to be acting. And what we're going to find with this example is that I've got forces, you know, using a right-hand rule. Let's see, magnetic field is into the page. Current is running up through the circle this way, through the half circle, and then back down. So if I do current, magnetic field, right-hand rule, the force is going to be off to the left. I'm going to skip the circular part, that looks hard. I'm going to come over to the other side and say here then, I've got current going downwards, magnetic field into the page, the force will be here. So what's happening here is this, I'm going to get forces all the way along this, and they're always going to be pointing off in that sort of outer direction. That's what the right-hand rule is telling me at each location. Now what's going to happen then, since these two portions of the current are symmetric, these two forces that they've labeled as ILB naught, those are going to cancel out. So if I'm doing an F net calculation, I don't need to include those. But let's see what happens along the circular path, and let's see if we can get any more usefulness out of here. I've got a center of the circle, I've got a coordinate system defined, and they've defined the radius as big R. And what they're doing is, they're saying, look, what I'm going to have to do at each point here is define an infinitesimal force. I'm going to have a series of infinitesimal forces, and they're going to be pointing in different directions. So I can't just add them all together. I actually have to look at their components first in order to do the addition. And the question becomes, what will happen when I add all those infinitesimal forces? So it's going to be some kind of an integration. And here it is. So here's what that is looking like. And what we have here then is, well, we have all the stuff we talked about before. Here is that curved portion with the current running through it. So let's concentrate on that. Now, I drew this in a different part of the curve, but here is the same coordinate system. I'm using theta instead of phi, which I guess works. So I'm defining this as theta equals 0 all the way to theta equals pi, or theta equals 180 degrees. And then here is the df. The df is lined up with this direction, from the center outward, so it's out in the radial direction. And then I've got a ds. Now I'm calling this ds instead of dl because that's what my calculus classes used. So there's a ds in this direction, and there's a force in this direction. The force is going to get divided up into components. So I'm going to end up with a cosine theta component that's horizontal and a sine theta component that's vertical. At the end of the integration, let's see what's going to happen here. By the time I've integrated all the way across here, all of the horizontal components are going to cancel out. Horizontal components, half the time they're going to be in this direction, and then the other half they're going to be this way. Those will cancel out. But the sine thetas won't. So what's going to happen if I add together all of the df's? The net effect is going to be upwards, and we can kind of see it from that diagram. The net effect of all of these forces is going to be in the upwards direction. Okay. So I set up the integration. So what I said was, look, I'm looking for the F net. The F net is going to be in the upwards direction. I can see that from my diagram. And the way I'm going to get that is I'm going to take each one of these little df's, but I'm only going to include the sine theta component. So I've only included sine theta, and I'm going to integrate that from 0 to pi. Now, using the formula for the force acting on current traveling through a magnetic field, we're going to scale that down to some infinitesimals and say if I take that one step at a time, so the ds, again, the ds are all these little paths that we're taking here. I can take I times b, instead of a full length L, I'm just taking this one ds at a time. And so that becomes my expression for the force. I've left off the sign of the angle, the orientation, because everything here is perpendicular. Let's take a look at that too. The current direction, the ds's, are representing the direction of the current, is like this. It's in the plane of the paper, whereas the magnetic field is into the page. And so at every location, I'm going to have 90 degrees. So I've left the angular factor off my cross product. So I'm getting a factor of IB. Now, I've got to integrate sine theta. So I've taken the ds, and the ds has been rewritten as RD theta. So that's kind of a standard way. We've seen that in, well, I don't know if in this class, maybe in Physics 4a, we use that a few times. We may have seen it in the electric field examples too. There may have been some homework problems with that. And you should have seen it in your calculus classes. So anyway, make sure you're clear on how that conversion takes place. And then I've got everything set up. So at that point, I can set up all of my integration. The I and the B are constant, and the R, they all come outside. I integrate the sine theta d theta, and that gives me a cosine, or a negative cosine. And then I flipped limits now, which you may, I do this all the time. I flipped limits, and so I'm evaluating the cosine from pi to 0. And what that means is cosine of 0 is 1, cosine of pi is a negative 1, and 1 minus a negative 1 is 2. So I picked up a factor of 2. So that should be telling us how much force we would get coming into this particular example. Okay. All right. Now we have already introduced this. The textbook is introduces the forces on currents first, and then it comes back and looks at forces on individual charges. So that's what's happening with the slides that we've got, and I'm maintaining their order. So here's the formula, right in the middle, very prominent. That's a good, we could probably get rid of the period. That, we don't need the period on that. So we've got the formula here, and then there's the right-hand rule, which I don't use this one. So my right-hand rule is going to look very different from this. You're welcome to use this one, but I'm not using that in the examples. Now what they're showing here is if I send these charges into a magnetic field, they're going to get pulled in opposite directions. I think we can get an easier diagram to see. So let's try it. Let's say we got a magnetic field set up like this. Now I'm sending these positive and negative charges in one by one. I'm not sending them in at the same time. So let's think, first of all, I'm going to send some positive charges in. And what's going to happen is if I send a positive charge in, this formula is telling me what force it will experience. So the force is going to depend on Q. It's also going to depend on how fast the charge is moving. If the charge is moving faster, there will be a larger effect. And then it depends on how large the magnetic field is. So as far as getting directions, it's going to be in the direction of V cross B. Now, if V is in that direction and B is into the board, then the direction on those positive charges is going to be here. Now, what happens with this charge is when it first hits the magnetic field region, there's a force here, and that means it begins to curve. Now, as it curves, the direction of the force changes right along with the orientation of the velocity. And what that means is, as this velocity vector curves, the force is always perpendicular. And that creates a curved path. So these magnetic forces are sideways. You know, we often think of forces as, hey, aren't forces just lined up between the two objects? And they're not. You know, magnetic effects very clearly have these sideways effects taking place. That's what direction these forces are in. So it doesn't speed up or slow down the charge if it's a uniform field. If it's a uniform field, it's not going to speed up or slow down the charge. It's just going to redirect it. Okay. And even, in fact, even if it's a non-uniform field, it'll just change the curvatures. So if it's a pure fundamental point charge with no spin, put in a few disclaimers here. Now, if it's a negative charge, let's try sending some negative charges in, and they're just going to have the very same thing happen, but in the opposite direction. And so I'm going to use a left-hand rule for this. So I go, hey, the charge is negative. Rather than using a right-hand rule and then flipping the direction, I can just use a left-hand rule up front. There is the velocity coming in, magnetic field is into the board, and then the force is perpendicular to that path. So you can draw that force diagram, you know, kind of like this. You can draw the force diagrams where if it's positive, the force is going to be perpendicular to the velocity in this direction. Here it's perpendicular to the velocity, but the opposite direction. Let's see. So I think they've got an example in here too, where they have a proton headed in some direction in a magnetic field, and there's a force. So the idea is this. There's a proton going in this direction. We can see that there's a force acting on the proton because it's curving to the left. And the idea is we should be able to determine, if we send charges through a magnetic field and we know that it's a bunch of positive charges, we should be able to figure out which direction the magnetic field is pointing in. All right, and so that's what's going on with this example right here. Now, let me jump ahead here. There it is. So here is the example, and what they're saying is that the magnetic field exerts a force. That's how much force there is. There's a certain speed given. And so that's kind of the example that I was working from here. I took the force, I took the velocity, I took the charge on the proton. The angle here, again, here's an example where the angle between the velocity and the magnetic field, once again, it's at 90 degrees, and the formula simplifies. So I was able to go back and set up the formula, solve for the magnetic field, and determine that the field was at 0.1 Tesla. All right. This slide is very quickly, it's saying if we just set a charge in a magnetic field, that's a lot to read. It just says if we place a charge in a magnetic field at rest, what force will it experience? And you go, none. Charges have to be moving. And the same thing is going to be true if it's positive. So just a reminder for us that the forces, magnetic effects require motion. So we need a charge to be in motion to generate a magnetic field, and other charges also need to be in motion to experience the effect of that.